Okay, so as promised, the solution to the mathnium problem. Your goal was to first find what was the decay rate. I'll show that. You should have found that it's decaying at a rate of 2%. And then if you start with a sample of 525 grams of mathnium, first set up that differential equation that would model the situation, and then you'll get an exponential function. Use that to figure out how long until there's 500 grams. So here's the solution. I should have said how to round. On the AP exam, they actually want you to round, if you round things, to round to 3 decimal places. So I didn't do that here. I didn't say how to round, so I just decided to go to the nearest hundredth. But realize on the AP exam, they would want you to go to the nearest thousand, so 3 places. So I probably should have put this to 3 places, but I didn't really think of it till just now. So just beware on the AP exam. That's what they would want you to do. All right, so the solution, I set up all the work. Basically, A is the amount of mathnium in grams at a given time, T, in years. Now, the way I got the percent decrease was to basically do like you would in like middle school. 100 grams became 98 grams. I need to know what level of loss that is. It's a loss of 2 grams. So it's 2 grams out of the original whole, which was 100 grams. So it's a loss of 2 grams out of 100 grams. If you lose 2 out of 100, you've literally lost 0.02 or 2%. So it's losing 2% according to this per year. And even though I'm going to call it 2%, we'll really work with it as its decimal form, 0.02. So now using the differential equation setup, the amount that I have left, or the rate that it's being lost, is based on the amount that I have. So the decay rate, basically what's the rate of change of the amount of mathnium I have, I lose 2% of whatever amount I had per unit of time. So a loss of 2% would be negative. So notice it actually works on the original 100. If I start off with 100 and a unit of time goes by, so if I start off with 100, well, I should lose 0.02% of it. That's the negatives for. So if I multiply the 100 by negative 0.02, I get negative 2. So basically, if I start out with 100 and then I change by negative 2, I've dropped to 98. So this differential equation represents the situation. How much mathnium am I losing? This is how much I'm losing. It's based on the amount that I have and that decay rate. So then from there, I solved the separable differential equation, which again, I didn't show all the steps, but if you've been seeing the videos, hopefully you're getting the idea by now. I divided that A over to put it with the dA, and multiplied that dt over. And then once I had the separable equation, I threw integrals on them and integrated them. Now I got natural log of absolute value of A equaled negative 0.02 t plus c. Once again, I got rid of the absolute value bars because the amount of mathnium I have is always positive. So I'm not going to be throwing in negative amounts, so I don't need the absolute value bars. And the way I got rid of the natural log was to do the trick where I did e to this power. Once I got this, remember this is a little hard to read, maybe negative 0.02 t plus c. That can be written as e to the negative 0.02 t times e to the c. And e to the c would just be another constant that we'd throw out front. So this is equivalent to this, which is your standard exponential decay equation because it has a negative up in the power. So I have A equals C e to the negative 0.02 t. Then I threw in the initial condition. I put that in red over here. Remember, times 0, I have 525 grams. So if I throw in 0 and 525, I solve that C is 525. So then I can make my actual equation. The equation for the amount of mathnium I have at any given time is 525 e to the negative 0.02 t. Now, to answer the final question, how long until I have 500 grams? Well, I throw in the 500 for the amount out using the starting amount and the decay rate according to this equation. Now, once again, I didn't have a lot of space. Hopefully you can solve this kind of stuff from pre-calc or having watched my last example. Just to go through what I did, I divided the 525 over, got that 0.95238, blah, 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 blah. It keeps going. Then I natural logged both sides to get rid of the e. So after doing natural log to both sides, I get natural log of that number. And then the natural log in front of the e lets that exponent jump out as multiplication. Then ln e is 1, so multiplying by 1 I don't really need anymore. Cancels away. Then the last step to get to t is to divide that negative 0.02 over. I did that. And like I said, I really should have, if it were an AP problem, I should have rounded to 3 places. I just rounded to 2 places. So I got approximately 2.44 years, and that's how long it takes to happen. So this is the entire process from defining it and coming up with the decay rate to using the decay rate in the differential equation to get the formula, and then doing some pre-calculus work to solve the formula for the amount of time it takes. So hopefully you got a final answer of about 2.44 years. All right. So that was the answer to the last problem. I said I was going to do an AP problem. I will put that in the third video because I need some more board space and I got to erase this. I only have 2 of these boards. Should have bought some more. But for now, that'll end this video, and then look for the last one. It will do an AP style problem with a differential equation a little more advanced than this.